So folks, how about another capacity test of a bunch of cells? Hi folks, I'm Roger from Offgrid, and in this episode I'm going to do a capacity test of these cells that we purchased from a lady called Annie in China. Reasonable price on these cells. I mean, they're not stupid cheap, they're reasonably priced, and thought we'd give them a bit of a go. And so here they are. We've unboxed them. I'm not going to show you taking them out of the box because that's just taking cells out of a box, but let's have a look at what we think of these cells. Nice little rubber covers on the studs. The studs are laser welded. These little collars here are tiny. I'm used to them being a little bit small. Our cells have reasonably smallish collars. We did some stress tests, some heat tests, and discovered there's no heat buildup whatsoever. But this is smaller than a small washer. It's probably just over 1 millimeter of collar on either side. So the challenge you have, if you look at these bus bars here, they elongated. The hole is elongated, and so when I eyeball this and just put it over here, there's a bit of lateral movement, but the ends are not making any contact. The contact area is tiny, it's really small, and I'm just wondering how they're going to perform under a stress test. It might be that you can't use conventional bus bars on here because of the incredibly small surface area of contact on this collar here. Maybe if you were going to use these cells, you'd need to use one of these flexible bus bars, because these don't need an elongated hole for obvious reasons, because they're flexible. So when I look at that, it's a bit of a much more snug fit, and it's going to have a lot more surface area. But we're not going to use this because this isn't what came with the cells. We're going to use conventional bus bars like this with the elongated holes. Until we tighten them down and actually strip one, we don't know how strong these studs are. We've seen some our laser welded studs of the cells that we use in our batteries. We've tested to 21, 22 Newton meters before they shear, which is a lot. And when we actually build the batteries, we build them to 7 or 8 Newton meters. And we've discovered there's no real difference between sort of 6 Newton meters to 8 or 9 Newton meters in terms of build-up, heat build-up, and the amount of current that they can carry. So these we would expect to probably need to torque down to at least 7 or 8 Newton meters. We've known of other laser welded studs that have sheared less than 10 Newton meters, so sort of in the area of 7 or 8 Newton meters they've sheared. So I'd be curious to see how these would perform, but we would only do that once we've capacity tested it, because it's quite a pain. Once you shear these things, it's quite a pain to put a helicoil down and fix them. Let's look at the general quality of the cell. So when we bought these, we were told that they were EVE cells, and so we're assuming these are EVE cells. As you can see, the label here says Vape Cell Technologies, so we presume that's Annie's company, or the company that she buys them from. We're assuming that they are proper EVE cells. We'll be able to check against the serial numbers, and so that's something we'll do a bit later. So they're 280 amp hours, and on the label, if I could actually, it's more difficult to read these QR codes than we used to. And I'm trying to see, yeah, they are 280, so LF280K. Very small writing to read that. So the QR code backs up that they're 280 and 3.28 volts. That's interesting because mostly on EVE cells they would just say they're 3.2 volts, but 3.28 is fine. The little bit concerned around. So this one here, this is already lifting up, so it's not glued down that well. Not too much of a problem, but we just like to see these glued down properly. This is a little bit tatty over here, not as neat as some of the cells that we've looked at, but as long as they perform well, that's okay. another interesting thing for me is if we actually put the pack, if we put them all against each other, there are two reasonable gaps here. So these cells are already bulging out a little bit. This one is completely flat here, with a gap forming there, but that could be because this black cover is slightly skew on the cell. So I think if the cover was straight, it would be just a small consistent gap. But definitely between these two and between these two, this gap is bigger than I would like to see for cells that have arrived at what should be around about 30% state of charge. So let's get to building this battery, charge the cells fully. We'll use an active balancer so that they're all fully charged, and then we will run the capacity test probably on a full built battery. So run it at 12 volts and see what we get out of it. I'm going to measure this bus bar. They're quite thin actually, so 1.3, 1.4 millimeters. So just over a millimeter, probably rated at 1 millimeter. It's a little bit of a ledge there that makes them feel thicker. If I compare them with our usual bus bars, we are 2 millimeters. So just over, call them a millimeter, ours are 2 millimeters. So in my opinion, not worth it, these bus bars. That's the surface areas. The cross section is too small to carry decent current. So I would definitely not use these cells with the bus bars that came with them. I would use them. Personally, if it was me, I'd use them with these flexible bus bars. I just want to see what the voltage is on these cells. .24, 3.24, 3.24, 25, 24, 3.24. So the cells are all alive and well. Go and switch on.
Look on the B minus.
Yeah.
Should we do it the other way around?
Oh, you know what? I had it the other way around. Okay, let's try and turn it on. It's turned on correctly. So,
Basics.
Monday morning, when it's not working, check basics. Absent-mindedly, I put P minus to the battery. I'm not used to having the BMS floating loose. We normally attach it before we do anything. So just remember, B minus goes to your battery and P minus goes to your load and charge. Let's get to the BMS app. And the settings will look correct. 280 amp hour. It says 3% remaining on the battery, but that's just because it was used for a test previously. Let's just assume it's going to be 30, but we'll leave the percent. We're going to charge it fully and it'll come up to 100% probably correctly. Resistance is good on these wires, 0.04, 039, 0404, so I'm happy with the resistance. Let's just double check some of these settings. So 3.6, 3.55. I know you can charge them to 3.65, but I'd rather just charge them to 3.6. The difference is absolutely minute between 3.65 and 3.6. So I'm happy with that, with those settings there. We'll charge maximum 200 and a discharge maximum 200. Temperature settings are fine. So we're good to go. Everything is on. And if I then measure with my multimeter, $12.97, so just under 13. So happy with that. Let's get it to charge right. We're back after about 4 hours of charging. So these were roughly a 30% state of charge when they got here. I think a bit less actually, and took about 4 hours to charge at 60 amps. So probably less than 30% state of charge. Now that they are charged, I'm looking a little bit at how much they have swollen. Because when this was put together, these were all in parallel. As you can see, the bus bar is holding these two together, but they've swollen, so this is forced out here. And although you can't see it very clearly in the camera at the bottom, they're forced quite far apart, so they've splayed out as a result of the swelling. Now, all cells do swell, but not as much as these. So I have to say that I am concerned with the degree to which these have swollen. We've known cells to swell much more than these, but the ones that we put into our batteries will only swell by about 1 mil, and this has swollen quite a lot more. So a little bit concerned about that. What I'm going to do now, I'm going to break the pack apart, and these simple testers are absolutely great for testing the capacity of an individual cell. So we're going to test all 4 cells with this to see what the capacity is of the individual cells, and see firstly how similar they are, and secondly whether they meet capacity. And the reason we're doing these individually is that if we test this battery pack as a whole, the BMS, this is a JK BMS, and this will kick in with its active balancer, and it will transfer from the higher to the lower cells, so that we won't be able to tell if the cells are reasonably matched. And we want to know if they are fairly uniform and fairly evenly matched. So let's get to it. We're going to strip this down and connect the 4 testers to the individual cells and see what they tell us. I am just zeroing all of these testers out because they still have the results of the previous test. So voltages 3.41, 3.4, 3.4, 3.35. So this is slightly down. These testers have 6 mil cables, and we're going to be doing a fairly low draw, so absolutely fine on 6 mil cables. So let's start with this one and get it going. So 10 amps. We are running the test at 10.2 amps, 10.1, 10.5 and 10.4. 10.5, make it the same as that. 4 testers running, and we'll see when they run it all down. Right, so the capacity test is completed. This one I reset by mistake, but it would have been about 287 amp hours, 287, 288, so well within capacity. It's bounced back to its resting voltage of 2.83. This one has gone 285.6 and back at its resting voltage, 286.3 and 285.4. All of them 2.6 to 2.8. So every single cell has met capacity. They are very close to each other, so in terms of consistency, very happy with that. You can see that the gaps between the cells have reduced. So if I push this one there, it's still a little bit of a gap, but not much. It's less and less of a gap. So happy with the gaps in the discharge state. But what we will be doing now is rebuild the battery. So we'll add the BMS back into the bus bars and charge this ready for a high draw test, so a real stress test to see how these perform. Right, so the battery is assembled with the same bus bars that came with the cells, which, as I said, are actually quite thin. But we will be testing these in a stress test. So I've just connected the BMS loosely. They're fairly thin cables just to do the charging at 30 amps, 31 amps here, according to the app, 28 amps going into the battery. So it's going to take roughly 10 hours, just less than 10 hours to charge this pack up completely at that rate. We'll let it just charge overnight, and then tomorrow I will torque these down. I'll put some washers on, torque these down, replace this with a much thicker cable, and then we'll do a test probably at about 160 amps just to see how these perform. I'll put a shunt on there to see just how much capacity we get out of them. So let's see. Back again a few days later, and I've totally charged the pack up, so it's fully charged, and we've connected it to an inverter. So I'm going to bring this on. I'll show everybody through. So here is the pack. Nipped down, all the bus bars are tightened down properly. They torqued down, a fairly thick cable running to the inverter positive, and then, well, that's a 50mm, but we've got a 35mm over here going from here to the JK BMS, and then the Guy and Dell leads coming to our smart shunt. So this is a Victron smart shunt, 500 amp smart shunt, going from there to the inverter, powering the positive from the positive terminal on the inverter itself. So here's our shunt is set up, and so what we're going to do now is we've got this simple old fan heater that's attached to the inverter, and we're going to fire all of that up. So let's start up I'm going to first just start recording this. So let's start up the inverter. There we are. Oh, and the heater was already on. So that's going full blast. And running at 172 point something amps, 171, 172 amps. So quite a high current draw. This is going to flatten this battery. It's a 280 amp hour battery, so just over an hour and 20 minutes or so. And this battery should be completely flat, and then we will know what the capacity is. So again, the idea is we want to test the capacity of these cells under a very high current draw. So as I said, 170 something amps, which is a pretty high current to be going through these. These are quite small bus bars, so I'll be interested to see how much they heat up. The gap, we'll bring the camera here, you'll see the gap between these two cells that are fully charged is fairly substantial, and they're actually touching each other. Less gap here and here. So that's a bit of a concern that one of these or both of the cells have swollen quite a little bit to, quite a lot to cause this gap here. Yeah, we will run this test for an hour or so and see where it takes us, see what the capacity of these is. So the test is running well. We're approaching 250 amp hours. I'm going to bring this down from roughly 190 amps down to half of that. So I'll turn this down just to give this a chance to get as close to its capacity as possible. If I run it at full ball 190 amps, the cells will reach their cutoff a little bit sooner, so just to be fair on them. But as far as the cells are concerned, yeah, we had the swelling, but when I just touch on the terminals, they're warm but not at all hot. So firstly, I'm surprised that the bus bars have held out so well, firstly, and secondly, with such a small collar, I didn't torque them very hard. I torqued them to about 6 or 7 Newton meters, and with such a small collar where this bus bar goes onto, I would have thought that with a reduced surface area that it would have quite a lot of heat buildup. But very impressed actually. And the cells they're warm, but they're not hot. You'd expect them to be warm. They can't not be warm at running at just under 200 amps. The BMS is quite hot. Let's see if I come and check the MOS temperature is 79. Granted, I haven't got double connections here, so I haven't got 2 cables, so there's a bit of heat build up over here. In fact, you can't really touch it, it's too hot to touch. So the MOS is quite hot, and that's quite hot, but that's nothing to do with the cells. That's just because I didn't use 2 cables, and these are known to heat up quite a lot anyway, so that's fine. This is also generating quite a lot of heat. The shunt would generate heat. That's what it's meant to do, really. So yeah, according to the BMS it's finished, but according to the smart shunt, we are now sitting at 255 with just about 25 amp hours left to go, 4%, and it's running really well. Supposedly we have 4 minutes to go. Let's see what the cell voltages are again. So we're dropping down quite rapidly. As you can see, we're at 2.6 something, and the diff has gone to 0.12, which is to be expected. So I'm going to turn this back one. In fact, it has just, I was just too late. I think actually the inverter has turned off because the voltage got too low. So let's turn this right off. Got this going again. It's only drawing and 96 amps now, so I'll give these a bit longer. And according to this, we're up to 11.2 volts. So obviously we're dropping quite a lot on these cables. That's quite normal. 11.2 volts, approaching to 40 amp hours. But at this rate it says it's going to be another 59 minutes, which is crazy. It wouldn't be that long. But yeah, we'll see what the final capacity is, but as I was saying, I'm quite impressed with the fact that these cells have not heated up a great deal, and it was actually the inverter that went to a low voltage cutoff, and nothing to do with the cells yet. And they're sitting at about 2.7, the lowest is 2.7 volts. I think it's due to cut off at 2.55, so it has a way to go. Right, we have concluded the test of these cells, and the big question is, would I recommend them? Yes, I would actually, because they have met capacity on the slow burn. So we discharged them individually at sort of 10 amps for a while, 15 amps for a while, and they all met capacity. They exceeded capacity, and they were quite similar to each other, so quite uniform. On the high burn, as you can see, we met 243.6 amp hours before the inverter shut down at low voltage. After a while, the BMS also turned off the discharge due to low voltage, so I've actually turned it on to emergency just to finish off the video. So 243, let's say it is about 245-ish. When you are discharging at such a high current, it is quite normal that they won't actually meet the same capacity that they showed when you do a low C draw. So I'm quite happy with that. We started off at about 170 amps, and then as the voltage dropped slowly, that increased until towards the end of the test we were at about 190 amps. So a very high C draw, and the cells didn't bloat terribly when they were being discharged. They didn't heat up. These very small collars actually carried the current very effectively. There's no heat buildup on the battery at all. In fact, the heat buildup was in the BMS and the shunt itself, but nothing on the battery. So quite happy with these. We'll put a link in the description below in case you're interested in buying them from a lady called Annie. The two negatives on it would be that they look a little bit tatty, but that's okay. But the biggest thing that I don't like is that they pushed each other apart. They pushed apart. You can see we've shown you the gaps between them. They're shrunk down now that they've completely discharged, so they'd be able to pack together. So if you were to restrain them with thread bar and ply ends or something, they'd probably be okay. But yes, they do swell up a little bit more than I'm used to. That's the only negative. But at $95 plus shipping, you can't go wrong. So they are fairly inexpensive cells, and yeah, I think that's good. So if I was to look at the JK app, as you can see, we've got to ranging from 2.6 to 2.8, so a fairly high delta, but that is quite normal when they are completely discharged below the lower knee. So I'm very happy with that. And well, that concludes it. So if you're interested in these cells, the description is below. And yeah, I think I'm quite pleasantly surprised. They have been pretty good. So yeah. See you in the next episode. Thanks, folks.